All right, so we're going to do some examples. This example is from Dr. Bob Selmer's notes, and this is a damped forced problem, vibration problem. So a damped system is subjected to a sinusoidal forcing frequency that can be adjusted. It is determined experimentally that at twice, let's say here's the part right here, it's like this word problem thing. Twice the resonant frequency, the steady amplitude is 1/10 that which occurs at resonance. All right, so that's almost like there's a word problem, that kind of thing. So you say that when omega f, it is determined experimentally that at twice the resonant frequency, the steady amplitude is 1/10 that of that occurs at resonance. So so another way of saying that is the x2 is equal to 0.1 of x1 if by which we mean or maybe you could even say that the this guy right here and that guy right there if you want, right? Here is the response is going to be 1/10 of that happens at resonance. So that's kind of like, another way of saying is that R is equal to omega F over omega N, which is equal to 2. It's a word problem. You have to kind of like study it a lot to quite get it. So here is like the basic equation that I wrote down on the previous notes. A version of it, like a shortened version. 1 minus R squared plus 2 times squiggle times R squared, right? So if you say, I'm just going to go ahead and, there's lots of different ways to write this, but this is the way I decided to do this. I'm going to say, I'm going to set these two things, one I'm going to set equal to 1, the other I'm going to set to 0.1, right? So I'm going to say that when this thing is equal to 1, oops, let me put it over this way. This one's equal to 1. This is going to be 1 over the 1 minus 2 squared plus 2 times squiggle times 2 squared, right? So that's going to be the input. Let's see, wait a minute. The steady amplitude is 1/10 that which occurs at resonance. Determine the damping factor of the system. Okay, so I said this one is equal. This one is equal to 1. So this is going to be equal to 0.1. All right, and at 0.1 we're going to have it's going to be resonance. Okay, so that means that R is going to be equal to 1. So here's going to be the square root of 1 minus 1 squared. Right? So that's going to be 0. Plus 2 times squiggle times 1 squared. Yes. Okay, so follow my logic here. That this thing over to the right-hand side, yeah, is going to be, on the right-hand side, we have resonance. And so this guy right here is equal to 1/10 of the resonance right here. So what we can do is now start canceling things out. We're going to find over here on the bottom over here, we're going to get 2 squiggle is equal to 0.1, yeah, times the square root. And then this guy right here, you notice he's going to be 1 minus of 4 squared, so it's going to be 3. 1 minus 2 squared, which is going to be 3. This is going to be squared, it's going to be 9 plus, and this one it turned into 16. I'm trying to remember how I got it into 16, but I did somehow. Oh, yes, this guy. 2 times 2, but squared, so 16. So 16 squiggle. I solved for squiggle, and I did it in a couple steps, but you can trust me that we get it equal to 0.1531, which is what they said this was right here. We're really just trying to play around with the numbers and try to think our way through a means that we can use this relationship with something that maybe we could observe. And we could maybe observe the fact that it was 1/10 and that it was like that we had that type of relationship. We could figure out and work backwards to find out what the damping was. I think I'm trying to rationalize this too much, but it is the sort of thing as an engineer would want to know, right? To be sort of an investigator, kind of like a Sherlock Holmes, where you see a situation and you're trying to figure out what the physical significance of it is, trying to come up and deduce what the nature of the system is. There you go. Rationalization. Let's do some more in another example.